This video introduces a catalytic alternative to the Grignard reaction that you learned in Chemistry 202Z. I show examples of alkyl lithium additions as well as organomagnesium halide additions to ketones and aldehydes, just to remind you about this chemistry. This requires stoichiometric preparation of butyl lithium or phenyl magnesium bromide, addition to a ketone or an aldehyde, often with careful control of the temperature, and with an anhydrous, aprotic, but polar solvent such as tetrahydrofuran. To isolate the tertiary or secondary alcohol product, we must use a dilute aqueous acid solution that quenches the Grignard reaction and protonates the alkoxide, which is the product of the first step. Although this Nobel Prize-winning chemistry, Nobel Prize 1912, has been heavily used over the past century, there are still some limitations, which are described on the lower part of the worksheet. The biggest problem with the Grignard reagents, and organolithium reagents as well, in addition to undergoing nucleophilic addition to the carbonyl, these reagents are also Bronsted bases and will deprotonate the carbon adjacent to the carbonyl as a competing reaction. In many cases, the energy barriers for both of these processes are similar. This challenge has largely been solved by a transmetallation reaction, so that the Grignard reagent or an organolithium reagent undergoes transmetallation with cerium trichloride to give an alkyl cerium dichloride reagent, which is much more nucleophilic than it is basic. The other problem with the Grignard reagents is that they are so reactive that they are not particularly selective for either face of a chiral aldehyde or ketone, nor have they given highly enantioselective reactions with achiral aldehydes or ketones. The trick here, another transmetallation, is to form diorganozinc reagents, which do not react with aldehydes or ketones at all unless they are coordinated with a chiral Lewis basic ligand. However, this requires two equivalents of the alkyl group, and so one equivalent is discarded as waste. The Grignard reagents are also highly reactive, so that if you have multiple aldehydes, or even distinguishing between an aldehyde and a ketone, the Grignard reagents tend to do a poor job of that selectivity. The best method for selective addition to an aldehyde in the presence of a ketone uses a catalytic reaction based on substoichiometric chromium and nickel using manganese powder as a stoichiometric reagent. The history of this transformation is described on the next page of the worksheet. This reaction was first discovered using chromous chloride. This is chromium in the +2 oxidation state, and was reported by Nozaki's laboratory, co-directed by Hiyama at Kyoto University in Japan. Initially, this chemistry was not all that reproducible, but eventually researchers realized that chromous chloride was generally contaminated with a small amount of nickel chloride, but the higher, purer grades of chromous chloride did not work in this reaction. This discovery was reported nearly simultaneously by Kishi's laboratory at Harvard University and by Nozaki's laboratory. Kishi has continued to work in this area, has published as recently as last year on an improved catalytic and enantioselective version of this transformation. An example from Nozaki and Hiyama is shown on the next page of the worksheet. Last semester, you learned how an organic bromide would undergo oxidative addition with magnesium to give the corresponding organomagnesium bromide. In this reaction, a ketoaldehyde is mixed together with the organic bromide, chromous chloride with a catalytic amount of nickel chloride, and in a polar aprotic solvent such as dimethylformamide or DMF, this reaction is complete within 3 hours. It does require an aqueous quench to protonate the alkoxide to give the secondary alcohol product. In the next video, we'll discuss the catalytic cycle in considerable detail.